it's not a graphing calculator, handheld graphing calculator, but it's a graphing calculator that graphs relations between x, y, r theta, t's, and all that. So I'm going to use that a little bit more frequently than pulling out my TI-8384 because a lot of the stuff that I'd like to do comes in a lot easier with this program. I don't want to sound like a commercial, but if you're interested in getting this, I think there's a discount for students. If you Google graphing calculator and type Pacific Tech, T-E-C-H, you might be able to see it. And I think if you convince this guy that you're a student, then you could buy it for like 20 bucks or 30 bucks. I'm not sure. But it's available. So we are in section 10.3 or 10.4, where we're taking a look at polar coordinates, and we have done a few of these objectives. We didn't really look at families of polar coordinates, but you can figure some of that out yourselves with the graphing calculator. I do want to take a look at a handful of graphs of things that might be interesting for us and the way to convert it. So remember, the relationship between polar coordinates and our more well-known Cartesian coordinates is something with a r and theta. So x is equal to r cosine theta and y is equal to r sine theta. All right, so let's take a look at a few graphs of things that might be interesting. Y is equal to 1. We know what that graph is, right? That's a horizontal line on the xy. On the xy plane. And if we're interested in writing this in polar coordinates, we should be able to by using this relationship. So when y is equal to 1, well, y is equal to r sine theta. So what we could do is we can write y is equal to r sine theta, but y is equal to 1, so let's just set this equal to 1. And then here's your relation between r and theta. In most cases, we like to represent r, or solve for r by itself, and represent r as a function of theta. So if we do that, you know, what's 1 over sine? Cosecant. So r is equal to cosecant theta. Okay? So in general, we want r as a function of theta. Now, if we believe that, we should be able to write r equals cosecant of theta and be able to see a horizontal line. And there you go, horizontal line. This seems to go on for a long time, going from 0 to 2 pi. Let's see what happens if we go from 0 to pi. That looks like it still goes on forever, huh? Let's see what happens. What's half of pi? 1.5-ish? From 0 to pi, it looks like it goes this way. Interesting. Okay? So with your actual graphing calculator, handheld graphing calculator, you can use that little tracer, that circle tracer, to draw this out to see where the values would be for different values of theta. I'm not going to do that right now, but you guys can try to figure that out. And we also showed that when we had theta was equal to something, pi over 3 or something like that, Do you remember what happened to this? What this turns out to be? This is a what? This is a line passing through the origin. So this is equivalent to y is equal to, I think it was square root of 3 times x, which is a line passing through the origin with slope square root of 3. Okay? We can confirm that as well using this graphing calculator program. If I type theta is equal to pi over 3, you see that little bit of a line. Now, because this is a function of theta and I'm not putting a restriction on r, the graphing program puts a restriction on r for me. It goes from 0 to 2. So if my r only went from 0 to 2, this is as far as my graph will go. But we can make this as large or as small as possible. Negative 9 to 9. I don't know why I chose 9, but that's more of a line there. Right? As far as I need to take this. Those are for my r values. Okay? Because theta is fixed, this is the ray that you're going to draw from, and depending on r, what r is equal to, this is going to bring you to wherever r needs to be. Okay? All right. So those are some graphs. They're not actually families of graphs, but if we take a look at families of graphs, one of the interesting graphs that we looked at was that, what's that graph called again? That gold graph that has a loop inside? Did you guys practice your French? Limaçon. And do you remember what that equation was? R is equal to something or other.
1 minus 2.
So I changed my limits to go just from 0 to pi over 2, 1.57. So if we take this all the way back to 2 pi again, 6.28. I get this figure. So when they talk about families of curves, what they want you to do is inspect what happens when you change a value of, let's call it a parameter, when we change one of these numbers. Let's say we change this into a 2. What do you think is going to happen? I lost my little loop. This was 1. This is 2. I lost my loop, and it looks like it went larger. This changes into a 3. Now it doesn't look much like a heart anymore. It's still a little bit, but not so much anymore. Right? So what's cool is that if you get a chance where you have a program that allows you to animate things, you should try to take advantage of stuff like that. So this allows me to animate things. And I think maybe if I go from 0 to 3. So if a is equal to 0, I have just negative 2 cosine theta. Remember what that was? Well, I think we graphed r is equal to cosine theta, and we saw that it was a circle. It actually drew this thing through the circle twice. So let's start changing the parameter a little bit. And then you see the animation part of it exactly at 2, somewhere over here. You have that cardioid, and then if you go a little bit further out, see, I only went up to 3. Maybe you should go up to 4. So let's see how this changes. And it goes out, and then at some point it starts looking like a bigger circle. It's not exactly a circle, but it kind of looks like this is how it would look like. Okay? So when they talk about families of curves, they tell you to change one of these values. In this case, we changed this A. We could have changed this number, and then we'll see another separate family of values. What do you think would happen if I change this from a cosine to a sine? Any ideas what do you think might happen? What? It would rotate. Remember the difference between r is equal to sine theta and r equals cosine theta? One of them is in the positive y, and the other one's in the positive x. So if we change this into a sine theta, it's going to be sideways or up and down instead of sideways. But the same story happens when you make the changes. Okay? So this program is called Graphing Calculator. It's available at the Learning Center. All the computers in the STEM Center, all the way in the back of the Learning Center, have this program that you can use if you're there. But if you don't, then see if you can get access to this or a different graphing program so that you can explore things a little quicker than your handheld graphing calculator. All right, let's call that done. Families. So now we got a couple of other objectives for today here. We want to explore the relationship between polar graphs and parametric graphs, and then find the slope of a point in the polar graph. Okay, I think those two objectives will help you do some of your homework problems. So I'm going to carry this around for a little while. After a while, you should have it memorized already. And just, simple equations that relate polar coordinates and Cartesian coordinates. So let's take a look at this in particular. X is equal to r cosine theta, and y is equal to r sine theta. And realize that in polar coordinates, a lot of times our function looks like r with some theta in it. So r is equal to cosecant theta. R is equal to, 1 minus 2 sine theta. So those are all examples of something where you have r by itself, and then you have some function with a theta in it. So the question is, how can we relate this into parametric equations? Now, if we look at this relationship between Cartesian and polar coordinates, we see that this is almost written like it's in parametric equations, right? Except x is a function of r and theta, and y is a function of r and theta. Now, in parametric equations, we're used to seeing x is equal to some function of t, and y is equal to some function of t. So if there's any way we can rewrite this relationship between Cartesian and polar coordinates so that x is just equal to a function of one variable, then we might have something there. Well, look at r. Right? What if we replace r with this? So then we would have x is equal to, instead of r, we'll use f of theta times cosine theta. And y is equal to r, and we'll replace that with f of theta times sine theta. Then, aside from the t and theta, well, that's just a dummy variable. Let's just call that t. Now we have parametric equations, right? That looked pretty easy. We have parametric equations. So we did stuff with parametric equations, like we were able to find the tangent line and things like that. So this would probably be helpful for us if we're interested in finding tangent lines to polar coordinate graphs. Okay, so that's all there is to it. So if you're in your calculator, if you're in parametric equation mode and you want to graph a polar coordinate, instead of switching to polar coordinate mode, you can just use this little trick to graph your parametric equations. So just to see that they do, in fact, work together, let's take a look at this graph. Let's fix a to equal to, let's just make it equal to 1 to make it easy. So let's take a look at this graph, 1 minus 2 sine theta. Now the way to do parametric equations here in this graphing calculator is to make these things called vectors. And then the x is going to have an x component. So let's say 1 minus 2 sine t. But that's just the f of theta, right? Oops, messed that up. Let's try again. I want this in parentheses. There it goes. So the f of theta function can go here, and for the x component, you would multiply it with cosine. And then similarly, you'll have the same f of theta function, except you would multiply it with a sine for the y. So if we graph this, right now my t is only going from 0 to 1. So this is all I'm seeing, going from 0 to 1. But if I let my t go from 0 to pi, I get this much. And then if I let t go all the way from 0 to 2 pi, I get the whole thing, right? And that's compared to, you can't see that graph anymore because this graph is drawing over it. There. Okay? So it's drawing the same thing. So we can think about this as your f of theta function, and here your x of t is equal to f of t times cosine of t, and then your y of t is equal to f of t. So f is just this function, except instead of putting theta in, we'll put t in, times sine of t. So this will constitute your parametric curve. Parametric form, and then you can adjust your t's accordingly. If you go from 0 to 2 pi, then that's your 0 to 2 pi for theta that you're doing. Now, you don't have to replace t, but it depends on the program that you're using. In the program that I was using, if I'm drawing a parametric curve, I need to use t. If I'm drawing polar coordinates, I need to use theta. A lot of programs are like that. They are specific to what your variable should be, depending on what kind of graph you're doing. In fact, in your calculators, if you press that x, t, theta, n button, it knows what to select depending on what mode you're in. But in general, when we're doing things by hand, you can really interchange t and theta. It doesn't matter. shouldn't make a difference. All right. So that's our first step, is to make that relationship between polar coordinates and parametric equations. Because now, if we're interested in derivatives, remember the dy dx business, that's a special formula for finding the derivative, the slope of the tangent line. Okay. Any questions? Are you guys understanding what I'm talking about? I have a couple of nods while I'm talking and stuff, but in general, I see a lot of glazed eyes. You guys have glazed donuts? All right. Yeah, you should ask questions if you have any questions. I hope this isn't like so weird and difficult that you can't even formulate a question. Ask questions while we're talking so that we can try to get things cleared up. All right, where were we? We were talking about derivatives. So we made the connection between polar coordinates and Cartesian coordinates by replacing the r with f of theta, whatever that function is, whatever that r function is of theta. And so now when we take the derivative, we just take the derivative. All right? Remember, the dy dx in parametric equations when you have x of t, y of t, the dy dx turns out to be dy dt over dx dt. And so if you apply that to our newly found formulas with x of t and y of t that came from the thetas, then it's essentially taking the derivative of f of theta sine theta. So the derivative of that, the derivative of the first times the second, plus the first times the derivative of the second, product rule. So that's a numerator. The denominator is a derivative of x with respect to t, or theta in this case. And so that would be derivative of the first times the second, plus the first times the derivative of the second. Derivative of the second is negative sign, so that's why there's a negative in between those two in the denominator. And that is exactly the dy dt dx dt that we had before. So now we have a formula for our derivative, or in this case, we might be interested in finding a slope of the tangent line for a parametric or for a polar curve. So, yes?
So this equation, there's no f plugged in yet. You would plug in like the f.
Yeah, so this is the general equation, and we'll apply it to our, we'll keep using that same limaçon that we were working with. Okay, so let's take this formula. Now we can find the slope of the tangent line. So let's ask that question. Find the tangent line. Let's go all the way to the tangent line instead of just the slope. I think most of the questions that they ask you just find the slope. Find the actual tangent line to the graph. Let's take our limaçon graph. One minus 2 sine theta. Ooh, theta. I'll put TH for theta. I don't have any symbols for this. And theta is equal to, and I need a specific theta to work with. And let's just say let's work with theta is equal to pi over 4 or something. All the things I decide to type, I don't have a typesetting thing for this. Instead of handwrite, I was going to handwrite it, and maybe I should have just handwritten it. All right. So this is our graph. Pi over 4, that's probably going to be, that's going to be tough to see. Maybe I should have thought about this a little bit more. You might actually be down here somewhere. You might have a negative r. All right, let's figure it out. I think that's what we'll need to do. So let's start with finding the slope. Find the slope. And so we need our r is equal to this. Let's rewrite r so that it looks like something that would be more math type. 2 sine theta. 1 minus 2 sine theta is r. So our x of t, I don't know if you guys want to go to theta or t if you're comfortable switching back and forth. I'm going to call this x of t and change a theta into t. So I have 1 minus 2 sine t times cosine t. So the first one is r cosine theta, the x. The y is equal to r sine theta. And r is equal to 1 minus 2t, or 1 minus 2 sine t. And according to my formula, I need the derivative of this. I guess you really don't need the formula if you just remember dy dt over dx dt, right? I'm just going to knock that out and just say, let's find dx dt and dy dt. So dx dt, dy dt. So dx dt, derivative first times the second plus the first times derivative of the second. So derivative of the first, the derivative of sine is cosine positive, so that's negative 2 cosine t. Derivative of the first times the second plus the first times the derivative of the second. Derivative of cosine is negative sine, so don't forget about that. Suppose we should take a step to try to simplify this a little bit. We have negative 2 cosine squared t, and let's distribute here. We have minus sine t minus, that's a plus 2 sine squared t. So one's negative, one's positive, and I'm unfortunately can't combine the cosine and the sine here, so looks like I'm stuck. We could do another trig identity thing where we could place cosine with 1 minus, or cosine squared with 1 minus sine squared or something, change everything to sines, but I'm not going to do that. So I was hoping for a cosine squared and a sine squared with positives or negatives, the same sign with the same coefficient, so I can make that into a 1, but it didn't happen for this one. So I'll leave it at that, and then let's do the second one. Derivative of the first, minus 2 cosine t times the second plus the first times the derivative of the second. This is where you get a negative. Oh, that's just a cosine. And let's see if we can simplify this. Minus 2 sine t cosine t plus cosine t minus 2 sine t cosine t. That didn't work either. That didn't help. I was hoping that this would have a 1 plus 1 minus and the same, but okay. Nothing simplified. Bummer. All right. So now the slope, I'm used to calling it m, so let's call it m. The slope is equal to the dy dt over dx dt. And then we want to evaluate this when theta is equal to pi over 4. I don't know if it'll help putting in pi over 4 now or later. Yeah, let's put it in now. I need to squeeze in some room over here. So dx dt, dy dt, let's put pi over 4 in there. Dx dt evaluated when t is equal to pi over 4. So for the first one, we'll put pi over 4. Pi over 4, cosine and sine and pi over 4 is root 2 over 2, right? So sine pi over 4 is root 2 over 2. It also is sometimes known as 1 over root 2. Root 2 over 2 is just like the rationalized denominator business. So the reason why I bring that up is because when you square it, it just becomes 1/2. So this is going to be negative 2 times 1/2 minus root 2 over 2 plus 2 times sine, so that's 1/2 again. So I believe if we do our math correctly here, this is equal to negative root 2 over 2. Okay, so that goes in my denominator. Right? That's that dx dt goes in the denominator. Dy dt goes in the numerator. So let's do that over here. Dy dt evaluated when t is equal to pi over 4. All right, we have negative 2, and now we have sine and cosine multiplied, but they're both equal to 1 over root 2. So let's call that a 1/2 again. Plus root 2 over 2 minus, same thing, right? Two times 1/2. So what do we have now? We have these don't cancel. Doesn't look like they cancel. So we have 1, 2, 2 plus root 2 over 2. Wow, whatever that is. Did I do that right? This too? Okay, anything else? So I suppose you could try to simplify this using algebra, but I think I'm fine with the way this looks like. So I got my slope. What do we need for an equation of a line? Slope and a point. We need a point. Oh, what's our point? How do you find a point?
Where would you substitute pi over 4 to the x of t and y of t?
So let's put t is equal to pi over 4 into x of t and y of t. So x of t, let's just say x of pi over 4. That's this thing, 1 plus 2 sine theta, cosine theta. So let's put pi over 4 in there. 1 minus 2 root 2 over 2 times cosine theta is root 2 over 2. So that turns out to be, I don't know, I don't think we can do much to simplify this. Something wrong? Did I do something wrong? Did you catch something? Did you catch something?
Oh, I was just thinking why it says that 2 shouldn't be like
This one?
5.
This one?
Yeah. No?
Oh, because this is 2 times 1/2, 2 times 1/2. I hope. You guys should check my work. I make a lot of mistakes. I make a lot of mistakes on purpose. So you guys should check my work. All right, so I think this is your x value and your y value. Pi over 4. When you put pi over 4 in for t, you get 1 minus 2. Sine pi over 4 is root 2 over 2. This time we have a sine. Well, it's going to be the same, root 2 over 2. So it looks like it's the same value. Okay? This looks a little bit unsatisfying because we get these weird numbers and we don't know if this actually worked out. So let's graph it. Okay, let's take a look at the graph. Oh, I hope this works. So we're claiming that our point was what? That's some weird number, right? Was 1 minus 2, or 1 minus square root of 2 times root 2 over 2. Some weird number like that. Okay, that kind of makes sense. If I drew a line y is equal to x, whoops, let's try that again. If I drew a line y is equal to x, which is theta is equal to pi over 4, right? That's your diagonal. Then we're looking like it passes through that line, so it looks like it's a negative number. If you, by the way, try to put this in your calculator, you should get a negative number, because it looks like theta is equal to pi over 4 is on the first quadrant, but this r value is bringing us back down on the negative side. And there's 2 of them, so there we go. And it looks like it's good so far. Now we need to look at this point and make a line out of it. So how do you make a line? Y remember how to make a line? Y minus y1 is equal to m times x minus x1. And what was our m here? M was minus 2. M is equal to minus 2 plus root 2 over 2
over negative root 2.
over negative root 2 over 2. Okay, this is kind of ridiculous now. Oh, my root 2 over 2 is not done correctly here. Root 2 over 2. All right, let's hope this works. Let's draw this in black. Does that look like a tangent line? Let's take that green line out. That looks pretty tangent, huh? Nope, did it. So you can punch all these things in the calculator and get numerical values and then use your graphing calculator to check it out. And remember, if this line that we just made up is a line in Cartesian coordinates, you can make this line into polar coordinates, or not polar, but you can make this line into parametric equations as well. So, all right, that's a nice picture. Let's take that. Let's take a picture of that. Put it in our notes. It's a little nervous there. I thought it wasn't going to come out right. Because if you mess up a negative sign, or if you're doing some algebra and you're, moving things around and you get one little thing wrong, then it's all messed up. Well, there you go. Okay, we need to talk about one more thing, and that is to be able to find areas of, not under the curve this time, but the areas between curves. And so finding that is a little bit trickier. And let me just show you what I'm talking about. Let's see if I can do this on the graphing calculator as well. And let's change our function a little bit. Instead of using this function, let's make a cardioid without a loop. Hey, Valentine's Day is coming up. You can make some polar coordinate functions and give it to your Valentine and say, hey, let's go polar tonight. Whatever that means, I don't know. So, if you're going to make this for your Valentine's, you give your Valentine a piece of your heart. You want to know what area you're going to give your Valentine's, or maybe your whole heart. I don't know what I'm talking about anymore. So what if you're going to give your Valentine a quarter of your heart? So we may be interested in finding the area of this. That's a small piece of heart. It's not a quarter, huh? A 16th. It's really small. Hell, we can try to figure out what this whole thing is. So you might be interested in finding the area of this little piece, and then maybe the area of the whole heart. Then you can tell your Valentines exactly what percentage of your heart you're giving them. So what we're interested in doing here is focusing on, we're going to use calculus, and the way we're going to use calculus is we're going to take a look at segments. What is this shape? If I have a circle, let's go from a circle point of view. If I have a circle and I want to find this area over here of the circle, and let's give this a radius r, and let's give this an angle theta. What's the area of this little piece of a pie, a sector, if you have a completely nice circle? What is it? I don't remember. R theta? That's the area? Well, we're doing something weird today, and so I'm just going to say we're going to stop here. We'll continue on with this for next time. What we're going to do is we're going to all go on a field trip to the Learning Center, to the STEM Center. So let's pack up your bags, and we're going to walk over there together. Now, what I want you to do is to think about what this formula should be, because I don't think it's this. This is the arc length. This is the length over here. So the actual formula for that area is a little bit different. So why don't you guys look it up, and then tomorrow's lecture at the beginning, you'll be able to tell me. Okay? All right, so that's it for today. We're going to walk to the Learning Center and walk all the way to the back to the STEM Center. And then we'll meet some people over there if you haven't already gone. Oh, I don't know if they have any more pizza at this time. Hopefully, anybody know? No? Okay. So maybe